Hello, and welcome to your second logistic regression in Python lecture. The first thing that I'm going to do, as per usual, is run all of my import statements. Now, hopefully what's below here looks really familiar because it's what we just did in our last lecture. But just as a review, I'm going to import our data set, which is looking at whether or not someone upgraded to a premium membership based on their age, their income, and the number of months they have been subscribed to the service. Now I'm grabbing the predictors, I'm doing a simple train test split, I'm z-scoring my data, being very careful not to have any data leakage. I'm creating my model, I'm fitting my model, and I'm using that fitted model to predict the values for the test set. Now, as per usual, once we have the predicted values, we can use them to calculate an accuracy score or plot a confusion matrix. And again, these give us similar bits of information, but when we look at a confusion matrix, we're often trying to see whether there's some systematic way that the model is misbehaving. So when it gets things wrong, is there something weird about the way it's getting things wrong? One thing to often look for is whether the model is predicting at some point both classes. If, for instance, these left-hand side was all 0, that would mean that our model was not really doing anything. All it's doing is always predicting that everyone upgraded, and that's not very useful. But that's essentially what we're looking for. Is there anything weird about the way the predictions for the model end up looking? Now, hopefully that's a review since you should have watched the last Python lecture. But I now want to talk a little bit about the coefficients because we didn't cover that in the last Python lecture. We can add our coefficients to a data frame the same way that we did for linear regression, and then we can look at them. Remember that the coefficients in the way that they come just straight from the model are in terms of log odds. And as confusing as log odds are, one nice thing is that positive values for the coefficients mean that variable, an increase in that variable, is associated with an increase in the probability of upgrading in this case. Variables that have a negative coefficient are associated with a decrease in the probability of, in this case, upgrading. So for instance, this is how you would interpret the coefficient of age in the case of logistic regression. We would say that a 1 unit, in this case unit is standard deviation since we z-scored, and that's very important to mention in your interpretation. A 1 standard deviation increase in age is associated with a 0.388 increase in the log odds of upgrading. Now, that's correct, but it's kind of difficult to interpret because who really has an innate understanding of what log odds are? So while we could totally look at this and say, well, income is negatively associated with upgrading and age and months subbed are positively associated, it can often be more useful to convert our coefficients to be from log odds to just regular odds. So the way that we do that is, well, practically by adding a row, or excuse me, a column to our data frame. We'll say coef bracket odds coefs equals, and all we're going to do is take the existing coefs column and exponentiate them. In other words, take e to the power of whatever the coefficient is. The way that we do that is with the mp.exp function, and we're just going to say coef bracket coefs. So we're grabbing the original coefficients, exponentiating them, and that's going to be our new column in terms of odds. Let's go ahead and run that and then print it out. And you can see now that we have a new column with our coefficients in terms of odds. So let's look at a practical interpretation. I know we spent a lot of theoretical time in the other lecture talking about what these mean, but let's talk about what it means in this specific instance. So in the case of age, we would say a 1 standard deviation increase in age, remember standard deviation because we z-scored, means that the odds will be 1.47 times the odds that it previously was. So for every 1 standard deviation increase in age, we will multiply our previous odds by 1.47. Similarly, every 1 standard deviation increase in income will be the previous odds times 0.994. And every time we have a 1 standard deviation increase in income, we will multiply our odds by 0.99. So hopefully that makes sense in how you can interpret the coefficients, both in terms of log odds or in odds. I will say that if you're presenting your results to people who aren't familiar with logistic regression or log odds in general, sometimes odds can be at least a little bit more intuitive for them. The next thing that I want to talk about is thresholds. So when logistic regression predicts a probability of upgrading, we will divide that somehow and decide that on one side of the threshold we'll predict a positive, so they did upgrade, and on the other side of the threshold we'll predict a negative, like they didn't upgrade. But the default that's usually used is 0.5, but we don't have to stick with that if we don't want to. I'm going to load in the new data and use that to show you how you can choose a different threshold instead of 0.5 if you like. So typically when we predict our values, we get out zeros and ones because the logistic regression model has kindly thresholded and put things in 0 or 1 for us from that continuous probability that it predicted. But we can actually ask the model for the predicted probabilities instead. The way that we do that, and I'll show that here, ypred prob, is by saying the name of your model, mylogit.predict x new z. But instead of predict, we're going to say predict underscore proba for predicted probability. Now let's just grab a couple of those so you can see what's going on. So when we look at the first 10 values, you'll first of all see one column on the left and one column on the right. This is essentially on the left-hand side the predicted probability of this data point being in the 0 class, so they didn't upgrade. And on the right-hand side is the predicted probability of being in the positive class, so they did upgrade. Now, because there's only 2 classes, all we really need is one of these columns, since the other column is just 1 minus the other column, but this will give it to you just both of them. For ease of computation, I'm going to go ahead and just grab the right-hand column, which will basically be the predicted probability that that person is upgrading their subscription. The way that I do that is ypred prob, we'll call it ypred prob 1, and I'm just going to say ypred prob, and I'm going to say give me all the rows, but only give me the right-hand side column. Remember, in Python, we begin indexing at 0, so this is the 0th column, and this is the 1 column. Just to make sure we did that correctly, let's say ypred prob 1, and look at the 1 through 10. So when we run that, you can see it's identical to that second column that we printed out originally. Now, when we typically predict 0 or 1, we would just look at this list that we generated and say anything with a predicted probability of above 0.5, classify that as 1, and if it's below 0.5, classify it as 0. In this case, everything except for the last row would be 1, and then the last row would get a predicted probability of 0. But instead of upgrading, say that we were predicting something like, does this person have heart disease, or does this person have the flu? In these cases, it's probably really important to us to make sure that we don't miss any positive cases, because we wouldn't want to send someone home telling them they're healthy if they are actually sick. So in that case, maybe we want to lower the threshold from 0.5 to maybe 0.3. That would basically make it easier to classify someone as positive, because instead of having to reach a predicted probability of 0.5, they only have to reach a predicted probability of 0.3 in order to be classified as the positive case. So one way we can do that is by using thresh. I'm just going to call this our threshold. We'll set it to 0.3. And then we're going to take our ypred prob 1 and we're going to say, okay, I want all of the values that have a predicted probability greater than 0.3 to be classified as 1, as the positive class. Well, the way that we can do that is by saying ypred prob 1, I'm going to call this we thresholded it. Oh, there we go. And I'm going to say y pred prob 1. So those are the predicted probabilities that they're in the positive class. And I'm going to say if they're greater than the threshold, classify them as positive. In this case, it's that they upgraded or whatever you're predicting. And remember, the greater than operator is a Boolean operator, so it'll give us a true or false value. But hopefully you remember from your 230 class that true and false values can just be treated as ones and zeros. The way that we actually convert them is by multiplying all of these Boolean values by 1. That way we'll get explicitly zeros or ones as our data. Just to give you a look at what this looks like, it'll say y pred prob 1 thresh, there we go, and print out the first 10. So you can see that all of them were classified as 1, which makes sense given what we've just seen, since all of them had a predicted probability greater than 0.3. So once we have those predicted probabilities, we could calculate, for instance, like an accuracy score, seeing how our predicted values did now that we're using a threshold of 0.3 instead of 0.5. So for example, I could say accuracy score, and then I have to give it the real values, which are stored in fashion, new, upgrade, and then give it our predicted values, which we've stored in y pred prob 1 thresh. So when you run this, we can see that we actually get about a 60.4% accuracy, which is not bad. And we could try other thresholds if we want, depending on our situation and depending on what we think is more appropriate. Accidentally misclassifying positive cases versus accidentally misclassifying negative cases. Because in some cases, like if someone is going to be accused of bank fraud, or we're going to predict something that could negatively impact someone, maybe it's important for us to raise the threshold, say to 0.7. This basically indicates that we have to have a very high predicted probability before we'll actually classify someone or something as positive. We could run that, grab our accuracy score. In this case, it's 42.2%, so it didn't do that well, but in a case where we want to be careful about classifying things as positive, sometimes raising the threshold is the correct thing to do. The last thing that I want to talk about is regularization. And if you've looked at the syllabus, you might be thinking, I knew we were going to cover regularization, but I thought we were going to do it in a couple weeks. And you're correct. I'm not going to go into much detail, but I do have to bring it up because the logistic regression function built by sklearn actually applies regularization by default. So when you don't change anything about the model, like here, when we're just using all the default arguments, you're actually using regularization whether you realized it or not. We'll get into more detail when we actually do the regularization lectures, but for now, all you need to know is that regularization basically makes our coefficient values a little bit smaller than they normally would be, and it does this in an effort to have a model that better works on unseen or future data. But for now, that's all I'll leave you with. What I want you to remember is just that this model default applies regularization. You can turn it off, and if you look at the two different cells that I have here, this top one is using the default, and it does use regularization since that, for better or for worse, is the sklearn default. In the bottom cell, however, I've set the penalty argument equal to none, which essentially tells the model, please don't apply any regularization to this model. Now, you can see the coefficients that I printed out for both these models, the first one with regularization, the second one without, and they're pretty similar. This isn't always the case, but this happens to be the case here. All I want to point out to you is that the coefficients from a regularized model are going to be just slightly different than if there was no regularization. It's often the choice that you would like to make, but I think it's really important to be aware of the default settings for the functions we're using, so I'm pointing it out here. Until we get to the regularization lecture, this will just have to be like a mental note, but just know that if you don't change the penalty argument, your logistic regression will apply regularization by default. Okay, hope you enjoyed that quick preview of regularization, but that's all I have for you today. I will see you next time.